All right. Now, I'm going to post all of these lecture notes online. And I'll post it in a format that you could print either one slide per page or 2, 3, 4, or 6. So you'll be able to print whatever format you prefer, depending on how much space you want to give yourself for notes. If you haven't already, it's important that you get the textbook because you're going to need access to the book not only to reinforce what you learn in class, but also to solve the homework problems. And your first real homework assignment is due a week from today. So you'll have until 11 a.m. on Tuesday to upload the PDF of Homework 2A. Lectures next week are online, as I already mentioned when we were looking at the schedule. So you know where to find those videos. You'll need to watch those videos in order to understand the homework assignment, so I'd really encourage you to watch those, and then specifically, as you're going through the video, pause the recording and work through the examples that are in there. You'll be best prepared for the homework assignments if you take the examples seriously, and so it's kind of like a stair-step idea. You start with the examples, then you get a little more practice with the homework assignments, and if you know how to solve the problems on the homework assignments, then I think you should be in a good position to do well on the exams. All right, so today we're going to, now that we've finished some of the introductory stuff, get into the technical material, talking about fluid properties and elasticity. Any questions before we move on? No? All right. Well, one of the good places to start is a discussion of units. And actually, if you have the textbook, on the front cover is a conversion. It's a list of conversion formulas between SI and traditional units. And we'll use both in fluid mechanics this semester, and probably we'll use SI units a little more frequently than we'll use the traditional British gravitational units. Of course, in the SI units we have kilograms, and in British gravitational units we have pounds mass, or slugs, as our units of mass, whereas we measure units of meters, and that's feet, inches, yards, miles. I always get a lot of laughs. I've taught overseas before. I've taught outside the United States, and when I tell them about the unit system that we use in the United States, they always scratch their head about 12 inches in a foot and 3 feet in a yard. They just think it's so ridiculous, and it is kind of ridiculous. Luckily, there aren't traditional seconds. Think of how weird that would be, as if there was SI time and there was traditional time. Who knows, maybe there'll be metric time later on where there's 10 hours a day and 10 seconds in a minute. Maybe there already is, but I don't know it. Where things get a little bit muddled is where we start to talk about units other than mass, length, time. Because all other units are derived from some combination of mass, length, and time. So a units of newtons, for example, is a kilogram accelerated 1 meter per second squared. A pound force is the corollary to that. We'll talk about how pounds force and slugs interact in just a second. For gravity, we'll use 9.81 for our SI, gravitational acceleration. Oh, do I not have 32.2? Well, it is. 32. Oh, here it is. All right. So pounds mass versus pounds force. Now, if we're working in SI units, a newton is the amount of force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. Now, in traditional units, instead of kilograms, we've got pounds of mass or slugs. So a pound of force is how much force is required to accelerate one slug at a rate of 1 foot per second squared. And a slug is 32.2 pounds of mass, which doesn't make a lot of sense until you remember that gravity is 32.2 feet per second squared, and so that's our gravitational acceleration. And so when you have gravity, when you have Earth's gravity, then a pound of mass exerts 1 pound of force. But if you're talking about any other acceleration besides gravitational acceleration, then 1 pound mass and 1 pound force aren't necessarily the same thing. But a pound of mass does exert a pound of force when it's just stationary on Earth, where we've got gravitational acceleration of 32.2. So, I mean, this won't be an issue a lot. We will occasionally have to remind ourselves what a slug is and how many pounds force it takes to accelerate a slug and so on. This is part of the reason why we work most of the time in SI units, is in the context of fluid mechanics, it just kind of like makes more sense a lot of times. All right, so weight is the effect of acceleration on mass. Today in lab, you're going to be examining fluid properties according to how much they weigh and trying to estimate the weight and mass of a liquid in a certain container. We'll be doing a brief hands-on activity in lab today and tomorrow. Temperature becomes important in fluid mechanics, particularly when we're doing stuff related to gases. And who here remembers back from chemistry the ideal gas law? I don't see as many hands as I expected to see. The ideal gas law, if there's one thing you remember from chemistry, as far as fluid mechanics goes, I hope that would be it. It'll come back to you. If you don't remember it, it'll come back to you. But we'll work in units of Kelvin a lot when we're doing gas stuff in fluid mechanics. And just as a reminder, the temperature scale of Kelvin, you have to add 273 to Celsius in order to get Kelvin. And the units of work and energy, we measure those in joules. And a joule is the amount of energy required to exert a newton of force over a length of a meter. Now, power is when we put a time aspect into the exertion of energy, and so it is how much energy is being consumed in a unit of time. And so a joule per second is a watt in the SI system. Okay, now like I mentioned, there's a lot of units conversion in the front of the book here. I'm also going to print out a units conversion that comes to you from the reference manual that's supplied for the Fundamentals of Engineering exam. Have you all heard of the FE exam before? You're aware that someday in the not too distant future, you're going to be sitting down in front of a computer to take that first engineering licensing exam called the FE. And so I'll give you a conversion sheet that comes from the FE, and you can use that conversion sheet during the exams, just to start to get you familiar with what the equations look like in that supplied reference manual, because it's really important for you to do well on that exam. Converting temperature, for instance, from Fahrenheit to Celsius is kind of weird, not only because the boiling point of water is different, but also the size of a degree is different. Fahrenheit degrees are smaller in size than Celsius degrees. They're only 5/9 of the size of a Celsius degree, in addition to the difference in freezing temperature and boiling temperature. We'll have an example in just a moment where we do some temperature conversions. In the gas law examples, if you're working in the traditional units, you have to use units of Rankine, and that's the absolute temperature scale for the British gravitational units. And over the summer, I started getting into baking, of all things. I don't know why, but just all of a sudden, I decided I wanted to try sourdough bread, making sourdough bread. And it's really interesting. I could go on and on about sourdough bread, but one of the things I'll tell you is that temperature is really important when you're making sourdough bread, because you're not just adding external yeast, you're actually trying to use your own yeast that you develop in a small culture, and then, see, here I go. But temperature is important in baking, and so I found myself over the summer doing calculations of, if you're adding flour and water together and they're both at different temperatures and you want the mixture to be a certain target temperature, how much heat do you have to add to the water? And so I was using absolute temperature because you get your calculations to work out when you use absolute units of temperature, that it wouldn't work out if you were using the relative scale of Fahrenheit like it would for raking. So, all right, just as give me a break from talking and give you a break from listening, let's try an example. If it was 46 degrees Celsius in Dubai last Wednesday, what was that in raking? So we need to do a temperature conversion here, and this is a multi-step temperature conversion. You're going to be going both from Celsius to Fahrenheit, and then from Fahrenheit to raking. 46 degrees Celsius. That sounds like nice and cool, right? No, it's extremely hot. All right. Now, I realize that a temperature conversion like this is as easy as just speaking the question into your smartphone, and then Google will automatically convert it for you. But they don't let you ask questions into your smartphone during the FE. So you actually have to know how to do this stuff. So we start off with 46 degrees Celsius. And remember, Celsius degrees are larger than Fahrenheit degrees. And so this 9 degrees Fahrenheit for every 5 degrees Celsius, we have to multiply this ratio to convert the number of Celsius degrees into the number of Fahrenheit degrees, and then also make the adjustment in the freezing point, because whereas Celsius, the freezing point is 0, the freezing point is 32 in Fahrenheit. So the conversion is kind of 2 stages, adjusting the size of the degrees and also adjusting the freezing point of the water. So if it's 46 degrees Celsius in Dubai, then people are enjoying 114.8 degree Fahrenheit weather. And that's summertime weather in Dubai. The conversion from Fahrenheit to raking then is just adding 460, which is the number of degrees. You have to go down from 0 Fahrenheit to get to absolute 0 in the raking scale. So everybody feel good about this one? Any questions? All right. Great. Now, fluid properties. We're talking about fluid properties today, and probably everyone's already familiar with the idea of density. And so a fluid that has a high density is something that would have a lot of mass per unit volume. And so can anybody think of a fluid that's kind of famous for having a high density? Mercury, right. It's a fluid that when I was real young, you kind of got to play around with. You know, you'd break open the thermometer to play with the mercury, but those were in the carefree days. Now, with modern safety regulations and everything, they put alcohol in the thermometers. I guess that could be fun too, but not from the standpoint of playing with mercury. So, yeah, mercury has a lot of mass per unit volume. Water has a density of 1,000 kilograms per cubic meter. Now, it varies as a function of temperature. And in the back of your book is a table that has fluid properties as a function of temperature. So if we go to appendix, I think it's A5, that has the fluid properties for water. Let's see if we can find it. There it is. All right, so A5 is the physical properties of water. So you'll notice that it changes as a function of temperature. So the density decreases as the temperature goes up. Anybody want to guess? Why do you think the density decreases as the temperature goes up? What's going on? The volume is changing. Yeah, so heating up water doesn't make its mass change. I mean, it would have to be one of these two things. If the density is changing, either the mass is changing or the volume. So like we take a kilogram of water and we heat up that kilogram of water. It doesn't become 1.1 kilograms because we heat it up. But what it does do is it it changes its volume. And so it's going to increase the volume as you warm the fluid, and that's going to decrease the density since volume is in the denominator there. So fluids, liquid in particular, vary their density as a function of temperature. Now, a lot of the problems you solve this semester aren't going to specify what temperature it is. You know, the problem sometimes will say 80 degrees Celsius water, and if it says some specific temperature, then you should go to the table and look up the density for that temperature. But if it doesn't specify, then just use the default assumption of 1,000 kilograms per cubic meter. That'll be sort of our standby water density. And if we're working in traditional units, then our standard density is 1.94 slugs per cubic foot. Of course, because what else could it be, right? All right, so that's mass density. Specific weight is related to mass density, except that instead of kilograms per cubic meter, we're talking about how many newtons of force are exerted by the fluid per unit volume. So using water as an example, water has a specific weight of 9810 newtons per cubic meter. Now, there's a familiar ring to the 981. What does that remind you of, 981? Gravity, right. So we go back here to the formula. It's saying that specific weight, sometimes this is also called unit weight. So it's saying specific weight is just density times gravity. And we'll use specific weight a lot in the equations that we solve because it plays an important role in everything from fluid hydrostatics to the acceleration of fluids. And so just multiplying the density times gravity can give us that specific weight. And so it's the weight of a fluid per unit volume. So water, if we have a cubic meter of water and we put it on a scale that's reading out in terms of the weight, which is a measure of force, it would say 9810, or if we had a cubic foot of water, then it would be 62.4 pounds of force is the force that's exerted there. All right, so maybe this is the first unique information. All the other stuff, I guess, is review from other courses, but maybe you haven't yet seen specific weight before. So there's your formula. Gamma is the density times the gravity. Compressibility comes into play here because it's one of the ways that we distinguish between fluids that are gases and that are liquids. And so comparing two common fluids, water and air. One of them is compressible and one of them is not. And so water is generally considered to be incompressible. Now actually, it's a little bit compressible, water is, but it requires enormous forces in order to compress water. As compared to air, air compresses really easily. When you drive around in a car that has compressed air in the tires, it's no big thing to compress air. But just the fact that we usually say water is incompressible, that doesn't mean that its density is always the same. Because, of course, we already talked about how density changes as a function of temperature. But then also, we can add salts and dissolve other things besides salts. We can dissolve things into water, and then that changes its density by increasing the mass that's in a certain unit of volume. Salt water, for example, has a different density than water does because it's got added salts in there. And so salt water has a density, instead of 9810, salt water has a density of about 10,000, slightly higher than 10,000, typical seawater. Specific gravity is when we measure the relative density or the relative specific weight of a fluid compared to water. So we talked earlier about mercury. You know, mercury is that fluid that is unusually dense. Mercury has a specific gravity of mercury is 13.56. So what that means is it has a density of 13.56 times the density of water, which we already know is 1,000 kilograms per cubic meter. And so a cubic meter of mercury would weigh 13,560 kilograms rather than 1,000 kilograms like water does. And so what this specific gravity is we're just trying to compare things to water as our baseline. And it doesn't matter if you have the ratio being a ratio of specific weights or a ratio of densities. So we always think about how oil floats on top of water, right? So the fact that it floats on top of water helps us to know that it's less dense than water. And so oils would have a specific gravity of less than 1 because the density of an oil would be less than the density of water. So sometimes it can be confusing in the problem statement because specific is a word that both can go specific weight and specific gravity. But there you've got the formula. You'll figure it out. You know, we'll start to use it, and then the confusion that you may feel now will gradually go away as you work more and more problems related to these. Any questions about these fluid properties so far? I'll try and keep an eye on time. I don't want to keep you late on the first day. That'd really be starting things off on the wrong foot, wouldn't it? I'll try to actually never keep you late. Here's what I aim for. I aim to start exactly on time and finish exactly on time. And I hope that you'll be here on time too. It really helps me out a lot because I'm so easily distracted if people aren't coming in and going out during the class lecture. So if you're here on time, I really appreciate that, and it'll help me. And if you're going to be late, you can always just watch the video, right? So yeah, don't come in late. Here's the table of fluid properties that I was mentioning. For those of you who don't have the book with you today, who didn't find it, those fluid properties are back in the appendix. This is table A5, which is for water. And it's showing both the density and the specific weight as a function of different temperatures. All right, here's the last topic we're going to discuss today, and that is the fluid property of elasticity. Now, just moments ago, I told you that water is incompressible, right? Well, here's the first time I'm contradicting myself. You didn't even have to wait like 5 minutes. Water is kind of compressible. And the way that we can measure how compressible a fluid is with a property that's known as the bulk modulus of elasticity. And what that specific parameter relates is it relates how much pressure is required to have a fractional change in volume. And I mean something specific by a fractional change in volume. What I mean is the amount of change of volume relative to the initial volume that was there before the compression began. I've got a calculation example here that I think will help to illuminate things, but this bulk modulus of elasticity tells us essentially how much pressure you need to affect a change in volume occupied by a mass of fluid. The bulk modulus of elasticity for water is 2.2 times 10 to the 9th pascals. That's really high. So it requires an enormous change in pressure to have a small change in volume. Now another way to think about this formula is, so dP is a change in pressure. So we can kind of like expand out this formula to say that the bulk modulus is the ratio of the change in pressure up here in the numerator, and then the fractional change in volume is going to be the initial volume here in the denominator of the denominator, and the dV. So you can have the dP is going to be some pressure that's applied. So let's take this as an illustration. Let's say that we started off with a sample of water that was 50 liters in volume, and it's open to the atmosphere. And so the 50 liters is our initial starting volume. And since it's water, we already know the fluid property that's going to be applicable here, the E sub V. We want to know what's the final volume that it occupies after we apply a pressure of 5 megapascals. So that's 5 times 10 to the 6th pascals that's being applied. So that's the delta P. And so delta P is the 5 megapascals. We can solve for the delta V that occurs and then apply that to the initial volume to find the final volume. So again, let me pause the recording, give you a few moments to calculate and collaborate with your classmates, and then we will revisit this to see if you get the right answer. Well, enforcing is probably too strict a word for it. I mean, sometimes I'll see students do, you know, like 49.886.54321.874, and I'll be like, come on. You know? It's like a reasonable. Yeah. All right, so what we do here is, first of all, our governing equation is this relationship between elasticity, change in pressure, and unit change in volume. So that's our governing equation that's given. We're given the initial volume of the sample, the fluid property that we need, and the pressure that's applied. And in the problem statement, it was using these, you have to know megapascals. You know, the interpretation of that is 5 times 10 to the 6th. So hopefully those already spring to mind. If not, then those are also in the FE reference manual that I'm going to be giving you. It reminds you all the engineering prefixes, you know, giga, mega, and so on, micro, nano. So rearranging the governing equation, because what we're going to want to solve for is this incremental change in volume, the delta V. So this negative sign that's remaining in the equation, what that negative sign means is that if you have the pressure increased, then the volume is going to decrease. So it's just kind of giving like a quantitative basis to what you'd already know on an instinctual level, that if you're compressing a liquid from all directions, it's not going to get bigger, it's going to get smaller. So that's what the negative sign there means. And so we have this delta V means it's the change in volume as a result of applying this pressure. So the change in volume is 0.114 liters. And so the final volume, 49.886 liters. And then what we could do, I guess if we're being careful about the units, it looks like we've got 3 significant figures here. 50.0 liters, 5.00 megapascals. And so my preference would be that you kind of like show all of the digits of accuracy that you've got, and then in the end you could round to 49.9 liters. So, you know, if you were measuring this with some sort of a scale that was only accurate to the nearest tenth of a liter, then what you'd see is 49.9 liters. But depending on the precision of the scale you're using, maybe you'd be able to read it to more digits than that. But any questions about the elasticity and volume change? Well, you know what? You can actually solve the first couple of homework problems. The first couple of real homework problems. In addition to that introductory assignment, you can get started on homework 2A, which is due on Tuesday. Probably I'm the only professor mean enough to give you homework on the first day, so all of your other classes, I assume that they gave you cake and you talked about your feelings and stuff. But so you had some time off in your other classes. You can get a head start in this class and, you know, really hit the ground running, do the introductory assignment, and all that other stuff. All right. Questions? Okay, so on Thursday, we're going to, you got to submit that introductory assignment by 2 o'clock on Thursday. And then we're going to continue talking about fluid properties. I'll see half of you in lab today, this afternoon, 2 o'clock. We'll meet in the lab. And then the rest of you who are signed up for Wednesday, I'll see you on Wednesday afternoon instead. Have a good day.